5.5, the substitution rule. If you will write a formula and you will have x somewhere in this formula and then you will differentiate it, you know how to do it and you will successfully get some other formula, right? If you will write an arbitrary formula and want to integrate it, well, most of the time you don't get another formula. Most of the time you don't even know how to integrate it, because many integrals cannot be solved analytically. They can be solved numerically. It doesn't mean that the integral does not exist. It just means that it's a very complicated process. And we often, even Nobel Prize winner will be unable to solve this integral for you. So naturally we are interested in those integrals that we can solve. Remember our table integrals. So here are our table integrals. How did we get them? Do you remember? We just took a function, kx for example, we differentiated it, we got k, and we said, oh, wait a second, it means that we can find antiderivative for k, and that would be kx. Oh, wait a second, kx plus c, right? So it started actually from differentiation process and it went backwards, right? So we wrote elementary functions and we found their derivatives, and therefore we knew the antiderivatives of those selected functions. Now we're still on a quest for the functions that we would be able to integrate. And the next step became chain rule. So remember the chain rule. If we have a composed function f of g of x and we want to differentiate it, we will get f prime of g of x, as if g was the whole variable. And then we have to multiply it by the inner prime, g prime of x. For example, if we will write a function sine of x squared, and we want to differentiate it, the derivative will be the derivative of sine is cosine of the same thing, right? We go the same thing. And then we go times x squared prime, inner prime, and that will be 2x. Therefore, if we integrate this function, we will get the sine of x squared, right? So when people realized that, so integral of 2x cosine of x squared dx is going to be sine of x squared, naturally up to a constant, right? So, and then when people realized it, they invented the substitution rule. And the substitution rule is the following. If you are looking at this, suppose you don't know how to solve it, and you are looking at all the patterns that you can see here. You can see pattern 1, which is the simplest, that would be 2x. The second that I see here is x squared. And the third that I see here is cosine of x squared. And this pattern is pretty complex. So it's cosine, and then, no, you can see that it's a composed function. So we don't want to pick composed function. We want to pick advanced pattern, like x squared. And we don't want to pick too simple. And sometimes it's obvious, because you can see that one pattern is a derivative of another. So that another pattern would be our choice for step 1. Step 1, set u is equal to a not crazy advanced pattern, but something that appears here. So I would say u is equal to x squared. Then step 2 would be compute du. What is du? It's a differential of u. And now we have to step a little bit aside, because in your notes they say, recall the differential of u is given by. And I have a strong suspicion that you don't recall any differentials, because maybe you didn't. We used to teach them in Calc 1, but then somehow they disappeared. So in case you don't know what is a differential, I want to tell you about them. So imagine that you have, I'll just draw it here. You have a function. That function, let's call it f, because we are more used to f. And that's your chosen x, and therefore this guy is gonna be f of x, the y coordinate. So by definition, differential of f is the change in f when x changed by dx. So let's say that this guy is x plus dx, and this point y coordinate is going to be f of x plus dx. Therefore df is going to be f of x plus dx minus f of x. So if we look at this triangle, where this is right angle triangle, this side is dx, that side is df, and this side is what? It's the tangent line, right? Because dx is very small. So we really have a triangle. Let me draw a little bit larger triangle. So df, dx. And note that if this angle is alpha, then tangent alpha is equal to df divided by dx, right, from this triangle. But on the other hand, tangent alpha is exactly our derivative f prime. So on the other hand, it's f prime. Therefore, if we have to solve this equation, f prime is equal to df by dx, for df, where df is differential of f, we just get f prime times differential in x. Differential in x is just an infinitely small step in x. So to compute, now if we call this function not f but u, du is equal to u prime times dx. So now we're jumping back here and we say, okay, once we set what will be our new variable u, let's compute du. To compute it, we need to u prime, so x squared prime, right? X squared prime times dx. So we do get 2x dx. A lot of times this is already enough, because you can say that I can carve out my 2x times dx. This is my du, and this is my cosine u. But sometimes it's more convenient to also do step 3. Step 3, solve the equation that you got in step 2 for dx. And you will get dx, in this case, is equal to du divided by 2x. And then instead of carving, you can substitute your dx. So naturally you will get the 2x, right? We are rewriting 2x times cosine. Instead of x squared, I would say u. And then I'm substituting dx, and that will be du divided by 2x. Now we are in for a very nice consolation. And we are getting cosine u du and a cup of coffee. So we do know how to solve it. That is going to be sine u plus c. And wait a second, we started with x's. We have to finish with x's. So it's good time to recall what our u is. Therefore, it's sine of x squared plus c.